All right, so for these notes today, we are going to be taking them on a line sheet of paper. So if we haven't done so yet, if we could take a second to pause the video and wait until everybody has a line sheet of paper or their notebook out to take our notes for the hour. So now that we're ready to go, we're going to title these notes Superposition Notes. Or just superposition. And up to this point, we've just analyzed single wave pulses for the most part, or wave pulses that are rhythmic or repetitive and simply just traveling in one direction. But you may have noticed, whether it be in our Slinky lab or in our waves on a string lab, if you have a end that is fixed, so something's holding the other end down, and you send a wave across the Slinky, you send a wave across whatever medium it is, it actually bounces back and it doesn't quite look the same like it does before. And sometimes even we might see the medium look all crazy. Again, like on our waves on the string lab, you have stuff bouncing up and down and moving in every which direction. So these notes are going to look at what happens when we have two waves interact with each other. We can predict what they're going to look like and how they're going to behave based on how they interact with each other. So in general, when a wave hits a fixed boundary, it is reflected and inverted. So when a wave hits a fixed boundary, it is reflected and inverted. By fixed boundary, we mean something is holding the other end of the medium down. The wave isn't allowed to travel on forever. In our waves on a string lab, you had a loose end so that the wave could be rhythmic and just kind of move on forever, and you can pause it as you go. When we were doing our Slinky lab, or at that point where I had to switch it to a fixed boundary, that is when the energy of the wave eventually is going to hit something and it's going to be reflected back. There's something there that's going to prevent the wave from moving on forever. So it gets reflected, so it bounces back, and then it becomes inverted. So inverted means generally to like flip upside down, but you could really look at it as flipping simply just direction or position. So what happens then when this occurs is that this causes different types of interference. So if something is interfering with somebody else, they're getting in the way of them. And that's basically what's happening here. You have two waves that are getting in the way of each other. So first, though, just so you can visualize reflection and inversion. So these types of problems that we're going to do, we're going to assume we have a wave pulse that's traveling through a medium. So let's say we have maybe a rope attached to the end of a wall. And so I snap the rope and it makes this wave pulse through the rope. And so this wall is my fixed boundary. So the wave's going to travel along the medium, and we're going to assume conservation of energy. So no energy is going to be lost as it's traveling. So it's going to approach the wall. And in my after, once it hits the wall, it's going to reflect back and then switch position. So in this case, the pulse was right side up, a crest. So it'll flip and become a trough and travel back along the rope. So I have this wave that is moving this way. It hits the wall, reflects, and becomes inverted. So we're going to see then, well, what happens then if while this wave is going this way, I snap the rope again, and we have another wave that's approaching it. So how can I predict how these two now wave pulses are going to interact with each other? So our principle that we use to make this prediction is kind of a long, fancy definition, but for the most part, after we do a few problems, should be pretty easy to use. So it's called the principle of superposition. Principle of superposition. So what this rule says is that when two waves interfere with each other, when two waves interfere with each other, the resulting displacement is the algebraic sum of the displacement at that location. So when two waves interfere with each other, the resulting displacement is the algebraic sum of the displacement at that location. So what this really is a fancy way of saying that when two waves interfere, we're going to add together their displacements. Now this is displacement, and remember displacement is a little bit different than like a distance. Displacement in this case is a vector quantity. So we can have positive and negative numbers based on position. So sometimes, even though this says algebraic sum, sometimes you will be subtracting because you'll have a positive number along with a negative number. So even though you're still adding them together, 2 plus a negative 2, you end up subtracting the numbers. So again, we'll look at some examples here, but in short, you're going to end up adding or subtracting displacements based on the position of the wave pulses. So we have 3 different types of interference, ways in which waves can meet up and interact with each other. The first is called constructive interference. Constructive interference. And so with constructive interference, when two waves meet, they have a displacement in the same direction. So when two waves meet and they have a displacement in the same direction. So by displacement in the same direction, we mean that this will happen when both amplitudes, so both of those displacements, amplitude is your displacement of your wave from rest, when both amplitudes are on the same side of the mean position. It's on the same side of the mean position, or if you like, you can make a little note, since they're interchangeable, the equilibrium line. All right, so we'll draw a picture to see like what exactly this looks like. When you think of the word constructive, constructive means, I think of like construction, so you're building something. So that's what's going to happen with these two wave pulses. They're going to meet up and build with each other. So their amplitudes are also on the same side of the mean position. So that also means then they're both crests or they're both troughs. So let's say I have one wave heading to the right with an amplitude of 2 meters. Oops, ideally they should be drawn about the same size here. Make this one a little shorter. All right, so this one here is heading to the left, so they're approaching each other, and they're both 2 meters tall. So this is my before. So as those waves approach each other, my during, so that split second in time when they meet up with each other, they kind of collide. Since their displacements are on the same side of the mean position, what that's going to do is both of their displacements are going to build. So that point where they meet up, we're going to add those two individual displacements together. So the two waves meet, they build to create one single amplitude. Now this isn't the new wave, because from our earlier readings and work with waves, we know that waves carry energy. So this is energy traveling through the wave, but they don't actually physically change or alter or move matter. So they're going to meet up for a split second, but then afterwards, they're going to continue to move on their merry way. So this one that was heading to the left will continue to move to the left. And this one heading to the right will continue to move to the right, but they will maintain their original displacements. So 2 and 2 on the same side, they meet up and build for a split second, have a resultant of 4 meters, and then they are going to pass through each other and keep traveling along the medium. This same idea of adding on both sides, we would do if these were both troughs. So if this was 2 below and 2 below, then when they meet up, they would build because they're on the same side. And this would just be a 4 meter trough once they met up. Our other type, as you can imagine, is going to be pretty much the opposite. So this is called destructive interference. And so with destructive interference, this is when two waves meet. And have displacements in the opposite direction. So when two waves meet and have displacement in the opposite direction. Now we have kind of two types of destructive interference problems. This is where we get our total of 3 types of interference. So we have the one type that's called complete destructive interference. And this is generally when you read or hear destructive interference instead of this other type, you're assuming then it's complete destructive. So with complete destructive interference, this occurs when both waves have an amplitude of the same size but opposite direction. So complete destructive occurs when both waves have an amplitude of the same size, but they're in opposite directions. So doing a before, during, and after like before. So start off with a before. So what do they look like as they're approaching each other? So let's say I have one wave that's approaching a fixed boundary heading to the right. The other one has hit the fixed boundary and now it's being reflected back. And let's say they both have an amplitude of 3, but one is a crest. So I have a 3-meter crest heading to the right, about to collide with a 3-meter trough heading over there to the left. So when these two wave pulses meet, they're equal in size, but opposite in direction. So they're going to end up canceling each other out. And for a split second in time, when they meet up, we're going to see the medium flat. So looking like it's simply just at rest, like there's no energy into the system. Because what we're doing here is we're treating one amplitude. Generally, the crest is treated as a positive amplitude or positive direction, like when we worked with displacement first quarter, and the trough as a negative number or our negative direction. So if this is a positive number plus a negative number, that's going to give you then 0 as an answer if we were going to add them up together. So that's exactly what we're doing here, even though sometimes you're given which one's negative and which one's positive, other times you're not, but you'll treat one as a negative value since they're on opposite sides of the medium. And conventionally, generally, crest is positive, trough is negative. So just like before, though, so these waves are traveling along the medium. They're not going to alter any matter, like they don't change matter, they just carry energy. So this happens when they're, like destroying matter. But so this happens for a split second in time. They cancel each other out, but then they're going to continue to move on their merry way. And so my crest that was, my trough that was originally heading to the left is going to keep going to the left. And then my crest that was heading to the right will keep moving to the right. So they meet up and cancel out for a split second, and then they just keep passing through each other. So my third type is a type of destructive interference, but it's a form of destructive interference when what happens if these two aren't equal in size. So what do we do? So we call this incomplete interference. And so with incomplete interference, you're going to treat it like destructive. So you'll have a positive and negative wave pulse, since one will be on one side, one will be on the other. But this happens when we have two waves that meet. That have unequal amplitudes and displacements in the opposite direction. So two waves that meet that have unequal amplitudes and displacements that are in the opposite direction. So doing a before, during, and after again. Get an idea of what these look like. So here's my before. So let's say I have a wave, again, that's 2 meters high as a crest heading to the right, but a 3-meter trough heading to the left. So these two here, they're in opposite directions, so we are going to end up having them kind of cancel out like in destructive interference, but they're not the same size. So I will still have a wave pulse that'll be made when they met, like in constructive interference, but it is going to be of a different amplitude, so different heights. And so it'll be less than the 2 since I will end up subtracting. But the side that it's going to be on is whichever is the larger side. So my during, when they meet up, I have 2 above, 3 below. So again, if we treat this like positive and negative directions, I would have a positive 2 plus a negative 3. So that would leave me with a negative 1 left over. So whichever side's the biggest is the side that the resultant will be on. So when they meet up, they're going to cancel out, except for that one little bit that'll be my trough at the end here. If the crest was higher, so the crest was 3 meters and this was the trough, then I could alter this 3 plus a negative 2, and that would leave me with a positive 1 left over. So that would leave me then with a crest during the meet. So whichever side is larger is where the resultant will be, and you'll still end up subtracting in the end because you have them in opposite directions. And just like with our others, so they meet up for a split second. And so at that split second in time, this is their single amplitude, but then they're going to keep passing through each other because energy is going to keep going. Energy doesn't get destroyed. So my after, my trough will continue to move to the left. And then my crest will continue to move on to the right. So that's our 3 types of interference. What we're going to do now at this point, we're going to have a practice that'll be handed out, and you're going to work on the practice. And then once everyone is pretty much finished up with that, I have a video to go over the practice and the corrections, and we'll check our work and see how we did. If this is still a little confusing to you after we've taken these notes and after we've done the practice in class, I do have a YouTube video with all this in action, and that would be a nice reinforcement for you if you still had any questions and if you were still confused after the notes in the practice sheet today. Otherwise, this is as crazy as it gets. So if you find today to be an easy day, obviously you can watch the video if you'd like, but don't feel like you have to if you don't want to, if everything seems to make sense. So that's it for the notes. We'll hand out the practice sheet now, work on that, and then we'll watch the other attached video.